Hi, this is the Science Chef. This video is a continuation of our solutions to the October-November 2019 Cambridge IGCSE Chemistry Paper 4. Today, we'll be answering question 2. If you'd like to watch our solution to question 1 of this paper, we have added the link in the description. Also, you can join our membership club to gain access to exclusive videos, live chats, and live tutorials from our channel. So let's start. Question 2 says, the gases argon, carbon dioxide, nitrogen and oxygen are in clean, dry air. Carbon 2 oxide, nitrogen 2 oxide, nitrogen 4 oxide, and sulfur 4 oxide are gases commonly found in polluted air. What percentage of clean, dry air is nitrogen? Give your answer to the nearest whole number. Alright, now let's underline the keywords in this question. The keywords here are gases, gas is present in the air, and what? Clean, dry air. Apart from that, we also have what? These gases here, which are considered as what? Pollutants in the air. So what is air? Air is a mixture of gases, and the constituents of air are nitrogen, which is 78%, oxygen, which is 21%, carbon dioxide or carbon dioxide, which is 0.03%, noble gases, which is approximately what? 1%, of which argon is the most abundant in the atmosphere, and water vapor, which is what? Variable, which has a variable percentage or proportion in the air, and then you can also have what? Dust particles. Now these constituents shown on the screen here are for polluted what? Air, right? Not for clean, dry air. But the question tells us that the air is what? Clean, dry air. Clean and dry, which means that water vapor and dust have been what? Removed. Fine. Let's now move to our question. What percentage of clean, dry air is nitrogen? So for clean, dry air, the percentage of nitrogen is what? 78.0%. Because we are asked to give our answers to the nearest whole number, that's 78%. You can say 78% or 78.0%, whichever one you're correct. Then you're now asked to name the process used to separate oxygen from clean, dry air. The process of separating oxygen from clean, dry air is known as what? Fractional distillation. Of liquefied air. Fractional distillation of liquefied air. Now, how does it work? The fractional distillation of liquefied air is separation of oxygen from clean, dry air. This process of fractional distillation of liquefied air is used in the industrial manufacture of oxygen and also industrial manufacture of nitrogen. Normally, the clean, dry air will be passed through concentrated alkali that will absorb the carbon dioxide from the air, right? Leaving nitrogen gas, oxygen gas, and the noble what? Gases. Then the air from which the carbon dioxide has been removed will be subjected to a series of what? Compression and expansion. Which will now force the air to liquefy, right? So when the air now liquefies, right, it will now be passed into what? A heated what? Fractionating what? Column, where the fractional distillation of the liquefied air takes place. The nitrogen will boil off first at about 196 degrees, minus 196 degrees Celsius. Then oxygen boils off later at about minus 183 degrees Celsius. So, and each of them will be collected into cylinders, different cylinders, and stored. So that's how oxygen is obtained from clean, dry air industrially. So next question. Before we look at the next question, this question here has 2 marks. So how do we end these 2 marks? 1 mark is for the word fractional, while the other mark is for the word distillation. So that is how you present your answer. Fractional distillation of liquefied air. 1 mark for fractional, 1 mark for distillation. Question 2C says, state one major adverse effect of the pollutant SO2. Now, here we underline these gases here, CO, NO, NO2, and SO2 as they are what pollutants in the air, because we have been told that there are gases commonly found in polluted air, right? And each of these gases has an effect in the environment, or in the atmosphere when they are released in the atmosphere. Like CO. CO causes brain damage. It's a very poisonous gas. Causes brain damage, suffocation, and death if the patient is not quickly attended to, right? It's a very silent killer. It is very, very poisonous, but it is colorless and odorless, right? Colorless and odorless. It's very difficult to identify it. You can just be in a place and be inhaling carbon 2 oxide or carbon monoxide without actually knowing that you are slowly moving closer to your grave. So it's a very, very poisonous gas, and it is formed in polyventilated areas where you have incomplete combustion of carbon compounds. And apart from carbon monoxide, we also have oxides of oxides of nitrogen. The oxides of nitrogen, that's the NO and NO2, cause acid rain. And how do they cause acid rain? Especially nitrogen 4 oxide or nitrogen dioxide. When it gets into the atmosphere, what happens? It dissolves in the moisture in the atmosphere to form an acid, a mixture of an HNO3 and HNO2, because it is an acid anhydride, or it is a mixed anhydride. Also, the nitrogen 2 oxide, that's the NO, nitrogen monoxide, is not stable in the atmosphere. When it gets into the air, it is easily oxidized to nitrogen dioxide. So it is nitrogen dioxide that will now react with the moisture in the air to form the acid rain, either in form of HNO2 or HNO3. Right? This acid rain is dangerous to plants or aquatic lives, right? It attacks buildings made up of, or structures made up of limestone. Also, it causes corrosion, and also these oxides of nitrogen also cause respiratory diseases. Then SO2, which is what we are being asked. SO2 being an acid anhydride, dissolves in the moisture in the air to form H2SO3, which is easily oxidized by the atmospheric oxygen to H2SO4, which is the acid rain. So the answer here is acid rain, and the effect of the acid rain is the same as what we have stated earlier for NO2. Now question 2D says NO and NO2 are produced in car engines. Fine. NO and NO2 are produced in car engines. Describe how oxides of nitrogen form in a car engine. Fine. Very easy. First off, nitrogen is a relatively unreactive element, right? But at high temperatures, it can combine with oxygen to form its oxides, right? So at high temperatures, naturally, it combines with oxygen in the presence of lightning. The presence of lightning to form nitrogen 2 oxide. Nitrogen 2 oxide. Now this nitrogen 2 oxide form is then oxidized by oxygen again, atmospheric oxygen to nitrogen 4 oxide. Are we together? Fine. So let's add 2 here. That's how the oxides of nitrogen are formed naturally. Now, when it comes to the car engines, right, what happens? Nitrogen and oxygen in the air that is used for the combustion of the fuel will now combine together at the high temperature of the hot car engine. The high temperature is provided by the hot car engine. The hot car engine does the same work that this lightning here does. That's the lightning here provides high temperature. So this high temperature is provided by the hot car engine, right? So the nitrogen and oxygen combine at high temperatures provided by the hot car engine to form the oxides of nitrogen. Let's write the nitrogen and oxygen in the air combine, or you can say react at high temperatures provided by the hot car engine to form the oxides of nitrogen. So the nitrogen and oxygen in the air combine or react at high temperatures provided by the hot car engine to form the oxides of nitrogen. Alright, how do you earn these 2 marks? 1 mark is for the source of the nitrogen and oxygen, that's air. Most students always make the mistake of thinking that the nitrogen used in forming the oxides of nitrogen in car engine come from the fuel. The nitrogen does not come from the fuel, it comes from the air, and of course oxygen is needed for the fuel to undergo combustion. So the nitrogen and oxygen in the air will now combine at high temperatures of the car engine to form oxides of nitrogen. So the source of the oxygen and nitrogen, which is air, will give you 1 mark, and then the high temperature of the car engine will also give you 1 mark. Alright, so question 2E. Question 2, it says many cars have catalytic converters. Let's underline that. Catalytic converters in their exhaust systems. In the catalytic converter, most of the CO and NO formed in the car engine is changed into less harmful products. Right? Identify these products and state the metal catalyst used. Now, a catalytic converter is simply a device, right, fitted in the exhaust of cars that will convert harmful gases produced during the combustion of the fuel, right, into harmless or less harmful products, right? So those harmful gases that are commonly produced are CO, oxides of nitrogen, which are NO and NO2. That's NO and NO2. And unburnt hydrocarbons. So these are commonly the 3 gases or the 3 substances that will move from the engine into the catalytic converter. So at the catalytic converter is made up of 2 chambers. It's made of 2 chambers. Something like this. Chamber A and chamber B. Now, those toxic gases coming from the engine, right? Coming from the engine and get into chamber A. And in chamber A, what happens in chamber A? Reduction takes place in chamber A. Reduction of what? Reduction of the oxides of nitrogen, that's NO2, is reduced to N2 and O2. Make these 2, make these 2. And also NO is reduced to N2 and O2. So these toxic gases, when they get into chamber A, the oxides of nitrogen undergo reduction to form nitrogen and oxygen, right? Now the CO, the carbon 2 oxide, and the unburnt hydrocarbon will not be affected in chamber A because it is only reduction that occurs in chamber A, and since these ones cannot be reduced in this chamber, they will move along with the nitrogen and oxygen to chamber B. And then in chamber B, oxidation takes place. In chamber B, oxidation of what? Oxidation of CO, right? The CO will now react with the oxygen produced in chamber A from the reduction of these oxides of nitrogen. So this oxygen here, this one and this one, will flow into chamber B with the carbon 2 oxide, right? And will now oxidize the carbon 2 oxide to carbon 4 oxide, or less harmful carbon 4 oxide, right? So make this 2, make this 2. Then the unburnt hydrocarbon, the unburnt hydrocarbon 2 will also be oxidized by the oxygen to carbon 4 oxide and water. So at the end of the day, what will be the product will be given off from the what? Exhaust pipe, right? This is the exhaust pipe now. From this exhaust pipe, nitrogen gas will be given off, CO2 will be given off, and water will also be what? Given off. Are we together? So that is how, that's a brief summary of the working of the catalytic converter. So coming back to our question, we are told to identify these products and state the metal catalyst used. So here we are only told that in a catalytic converter, most of the CO and NO form the kind of fine. So our focus here is on CO and NO. We are silent on the unburnt hydrocarbons. So we will provide answers based on what is given to us in the question. So the CO would be converted to CO2 or carbon dioxide. Since we are told to identify, we're not told to name, so the formula will be okay, right? CO2 and nitrogen, that's carbon 4 oxide and nitrogen gas. Or if you like, you can write out the name: carbon dioxide, carbon 4 oxide and nitrogen gas. Those are the product, the less harmful products. The catalyst used can either be rhodium, platinum, or palladium. Any of these will be correct. They are all transition metals. So if you write any of them, you are correct. The symbol of rhodium is RH, capital RH. Platinum is capital PT, while palladium is capital PD. Being transition elements, one of their chemical properties or unique properties is possessing catalytic ability. So we move question 2F. Question 2F says CO is formed from the incomplete combustion of fossil fuels such as methane. Write a chemical equation to show the incomplete combustion of methane. Okay, so I've already explained how CO is formed, so which is what they are also stating here. So methane, what's the formula for methane? Methane is an alkane, and the general formula for alkanes is CnH2n plus 2. Yes, and when N is 1, methane is the first member of the alkanes. This is the N will be what? 1. When N is 1, this formula will change to what? C1H2 into 1 plus what? 2. And that gives us what? CH4. Yes. So we do that. CH4 gas plus oxygen gas will give us what? Now, being a compound of carbon that undergoes incomplete combustion, right? It will form what? CO, carbon 2 oxide or carbon monoxide, as already stated in the question, and water from this hydrogen, since an alkane. Yes. So now we are told to write a chemical equation to show the incomplete combustion of what? Methane. This equation of balance. Let us see. Carbon here is 1, carbon here is 1. Carbon is balanced, hydrogen here is 4, hydrogen here is 2. So hydrogen is not balanced. When balancing equation, it's always advisable to balance the atom standing alone last, right? So hydrogen here is 4, hydrogen here is 2. So what do we do to this to make it 4? Multiply by 2. We add 2 here. So hydrogen is now 4. Oxygen is 2. Oxygen here is what? 2 plus 1, 3. So oxygen here is 2. So what can we do to this 2 to make it 3? If you multiply it by what? 3 over 2, right? So let's write it out somewhere. That will give us 3 multiplied by 3 over 2. So you multiply by 3 over 2, we need to clear the fractions, right? So since we cannot balance equations using word fraction, we balance chemical equations with whole numbers. So to clear this fraction now, we will multiply through what? By 2, and we do that. This will be what? 2. This will be 3. This will be 2, and this will be 4. Good. So our equation is what? Balance. Let's see. Let's confirm. Carbon here is 2. 2 times 1, 2. Carbon here 2 times 1, 2. Hydrogen here 2 times 4, 8. Hydrogen here 4 times 2, 8. Oxygen here 3 times 2, 6. Oxygen here 2 times 1, 2. Then plus 4 times 1, 4. 4 plus 2, 6. So everything is balanced. Correct. So let's move on to the next question. So question 2G says the CO2 in air is part of the carbon cycle. Carbon cycle. The carbon cycle is just a part that shows the flow of carbon 4 oxide, right? The flow of carbon 4 oxide into the atmosphere and out of the atmosphere, right? So then the scheme shows a simple representation of part of the carbon cycle. In this scheme, we have from carbon dioxide in the air to glucose found in green plants, right? Then from glucose in green plants to animals, then animals back to carbon dioxide in the air. What does this mean? It means that plants use upward carbon dioxide in the air to produce what? Glucose. Can you see? That's what this representation means. Plants use up carbon dioxide in the air to produce what? Glucose. And what is that process called? The process by which green plants use up carbon dioxide in the air, right, and water in the presence of sunlight to make their food is known as what? As photosynthesis. Okay, so let's just write here. So this process here is photosynthesis. Fine, still come back to it. Then here, so when the animals now feed on the green plants, they will now take in the glucose. And of course, glucose is carbohydrates. What do you use carbohydrate for? For what? Energy, right? And when they do some work, right, that glucose will be converted to what? Energy. Through what process? Through the process of what? Respiration. The glucose will be broken down into what? Energy. And the CO2 will be given off as a what? As a waste product, which is now released into the atmosphere again. So now I'm going to state the scientific terms for each of process A and process B. Wow, we already answered the question. So A is what? Photosynthesis. Photosynthesis. While B is what? Respiration. Wow, great. Let me quickly write the equation for respiration here. Respiration is C6, breaking out glucose, C6H12O6 plus oxygen to give us what? CO2 plus H2O, then plus what? Energy. Plus energy. How do we balance? Is it balance? Carbon here 6, carbon here 6. Hydrogen 12, hydrogen here 2, so hydrogen will be what? 6, that's 12. So oxygen here is 12 plus 6. Oxygen here is 12 plus 6, 18. Here oxygen is 6 plus this 8. But if considering this alone, this is 6. How can we make this? We need 12 to make this 18. So we multiply this by what? 6. Good. So that gives us the equation for what? Respiration. That's the breaking down of what? Glucose to release what? Energy by living organisms, right? Fine. And you can see that this process, this equation, is the reverse of photosynthesis. Just that here we reverse this equation where CO2 and water become the reactant and glucose and oxygen become the product in the presence of sunlight and chlorophyll, right? We'll get what? The equation for photosynthesis. Right. So let's move. The next question says plants convert glucose into complex carbohydrates. glucose, of course, is a carbohydrate. It's a type of carbohydrate. But glucose is a simple carbohydrate, or what we call a monosaccharide, right? Fine. So this question says that plants can convert this glucose into complex carbohydrates like starch. And starch is a polysaccharide, a complex carbohydrate. Other types of complex carbohydrates are cellulose, glycogen, chitin, and co, right? While other simple forms of carbohydrates like glucose are fructose, galactose. We have the disaccharides, the sucrose, the maltose, and the lactose. Fine. So we are told that the unit of glucose can be represented as this, right? Glucose belongs to what we call the aldose family, right? That's more or less like the aldehydes with hydroxyl groups, fine. We call them the aldose. While the isomer of glucose, which is fructose, belong to the ketose. That is the fructose contains the ketone functional group, right? So we are told to complete the diagram to show the complex carbohydrate formed from 3 units of glucose. Show all of the atoms and all of the bonds in the linkages. Now, carbohydrate is what we call a condensation polymer. Carbohydrate is a condensation polymer. And what is condensation polymerization? What is polymerization in the first place? Polymerization is the joining together of small organic molecules called monomers to form large organic molecules called what? Polymers, in the presence of what? High temperature and high what? Pressure. Good. That's polymerization. Then there are 2 types of polymerization: addition polymerization and condensation polymerization. So these are the 2 types of polymerization: addition and condensation polymerization. But this question is on condensation polymerization. Let me quickly talk about addition polymerization. Addition polymerization occurs in compounds that have what? Double bonds. Examples: the alkenes, the unsaturated what? Hydrocarbons, or any compound with a carbon-carbon double bond can easily undergo what? Addition polymerization, right? So that's aside. Now, condensation polymerization occurs in molecules that have 2 functional what? Groups, like this and this. You say they are what? They are bifunctional. Molecules that are bifunctional, like diols, right? Like diols, dicarboxylic acids, diamines, etc. All these compounds can undergo condensation polymerization because of their 2 functional groups per molecule. So if these molecules were to combine to form a complex molecule, in this case now a glucose molecule, 2 glucose molecules combining to form a complex carbohydrate, right? Now, condensation polymerization is the polymerization that occurs with the elimination of a small molecule. In other words, small organic molecules known as monomers join together to form large organic molecules, right, called polymers at high temperature and what? High pressure, with the removal or elimination of what? A small molecule like water, like ammonia, like hydrogen chloride, depending on what the monomers are. So if these 2 molecules of glucose were to combine, let me draw a small structure here. So this OH here and OH here. If this were to combine with another glucose molecule here, what do you think will happen? Something will have to be what? Eliminated, and that is what? Water. How can we eliminate water here? It means that one of these will lose its OH, while the other one will lose the what? The hydrogen what? Atom. So, and these 2 will combine what? To give us what? Water, right? Great. So when that happens, the next one that comes will also what? Do the same. This hydrogen will also go, and the OH of the next monomer will also combine with this hydrogen to form what? Water. So at the end of the day, we have something like this. So if this were to combine, there will be an O here, right? There will be another O here. Remember what is lost here from what we have done here. OH. This one loses what? OH right here and loses what? H here. Are we together? So this one loses OH here and loses H here. This one loses H here and loses OH here. Right? Since this one is losing OH here, there will be no oxygen at this end. Right? So there will be no oxygen there. So just be what? A straight bond. And since this one is losing only hydrogen, there will be what? Oxygen with an extension there to show that it does what? It continues, and that is the structure of the complex carbohydrate. Remember, we are told to do what? Complete the diagram to show the complex carbohydrate formed from 3 what? Units. To show the complex carbohydrate formed from 3 units of glucose, right? Then show all the atoms and all the bonds in the what? Linkages, which is what we have done here. So for showing all the oxygen atoms here in these linkages, we get 1 mark. Then for showing these bonds here at the end, these extensions at the end here, and another mark. Question 3. Question 3 says complex carbohydrates break down to form simple sugars, right? Polymerization is the combination of simple molecules known as monomers to form what? Larger what? Or complex what? Molecules called polymers, right? Now, the reverse now is what we are talking about. The breakdown of those complex molecules into simpler what? Molecules or smaller molecules is known as what? Hydrolysis. The reverse of polymerization, or the opposite of polymerization, is hydrolysis, right? I told to state 2 ways that complex carbohydrates can be broken down into simple sugars. First is by boiling. If you boil starch in the presence of an acid like HCl, we will obtain glucose, right? Starch. We have starch here, and we boil it in the presence of water / HCl, we get what? Glucose. This process is called what? Acid hydrolysis. Acid hydrolysis, because it occurs in the presence of what? An acid, that is acid HCl. And hydrolysis is using water to break a compound into smaller or into simpler what? Units, right? Then the other method occurs inside our body in the presence of what? Enzymes. That's enzymatic hydrolysis, or what we call digestion. Fine. The last question says, name a suitable technique for separating and identifying the individual sugars formed when complex carbohydrates are broken down. After breaking down or hydrolyzing the starch into simpler glucose molecules, right? And we have to use a separation technique to identify the individual sugars formed. In other words, there will be a mixture of sugars. That's what this statement is trying to say. There will be a mixture of what? Sugars, and we will need to identify them. So, and the method that we can easily use to identify these sugars after hydrolyzing the starch or any complex carbohydrate is chromatography. You can use what? Chromatography. You can use chromatography to identify them. After the hydrolysis, after the resolution has taken place, you can use a locating agent such as anhydrine. You can spray the chromatogram with a locating agent such as anhydrine to easily identify the spots of the separated sugars. So the answer is actually what? Chromatography. We will treat chromatography in details when we'll be answering questions on the alternative to practicals. Ensure you keep a date. So that brings us to the end of our solution to question 2 of the 2019 October-November Cambridge IGCSE Chemistry Paper 4. If you know you learned anything from this tutorial, hit the like button and leave a comment. Also, if this is your first time here, don't forget to subscribe to our channel and turn on the notification bell to always stay updated with our new uploads. A wise man once said, "The truth is like a lion. You don't have to defend it. Let it loose to defend itself." So always stay truthful at all times till I see you when I'll see you.